cloud. Prestazione in corso. Sono sicuro che sia perfetto, comunque non importa, si vede sufficientemente bene, diciamo. Anche perché ho fatto lo zoom, io qui non vedo. È un autofocus? Non vedo il focus, c'è un auto setup, non vedo. Non facciamo casino, va bene così. Meglio è nemico del bene. Poi it works, don't touch it. No, dicevo se lo volevi anche. No. Aspettiamo proprio i 30 e poi facciamo scena. Sì, va bene. Okay, it's time to start again. So we go on with Pallavicini and Neutrino Phenomenology.
So thank you. We were here about propagation and the mass effects linear in the electricity and squared in the mixing. Let me just finish the comment on this slide showing that, telling and repeating that sterile neutrinos must exist. The question is not whether there are sterile neutrinos, because either you have a Majorana partner or you have the right-handed neutrino, but you do need them. The questions about sterile neutrinos is whether they are light or not. This could be very heavy and completely decoupled from standard model, or could be light, we don't know. And whether they are mixed or not with the other ones. These are the questions, but the existence of sterile neutrinos is no question. Oscillations. Again, I assume you know what we are talking about. If you have the three flavors mixed, the mixing induce the M-square effect that I mentioned. These are the specific formulas. It's in the simplest way is to solve the Schrödinger equation with three flavors, assuming mass against states, and momentum against states, energy, blah, blah, blah. You get this formula. This calculation is beautiful and wrong because it's written in many places, but there is a contradiction in using fixed momentum states and assuming oscillations, because if you have exactly defined momentum, there cannot be any oscillations. The reason why this calculation is often reported is that the result is right. So I would not have put it there in the yellow box. You should do the calculation with plane wave with the buckets correctly, but the result you get is identical to this not correct calculation. So it's not so serious, but this is anyway an idealistic case in which you are not considering the loss of coherence. That's why you should use wave packets, because if you do the calculation properly with wave packets, you get this formula, but you also understand that this formula has an exponential decay of the oscillation due to the fact that at some point, the fact that the momentum is not perfectly defined make a coherence loss. So at some point, you don't get any more oscillations, but you get a mixture of neutrino flavors. So when you do properly the job, you have to include the fact that at some distance, the coherence is lost. I will not elaborate too much, but it's important that to do an oscillation experiment, you have to be far from the source, but not too far, otherwise the oscillation is lost. So I finished the theoretical introduction, or let me say the phenomenological introduction. I did not do any theory, but I have recalled some specific theoretical element. I have recalled the main neutrino properties. Now we go to the experimental physics. This is just a plot of the fact that we have been discussing about neutrinos for almost a century. 6 years from now, we will have the 100th birthday of neutrinos. Many things have happened, ideas, main properties, helicity and parity violation, more than one neutrinos in the 60s, solar neutrinos beginning exploration in the 70s, supernova neutrino detection in 87, solar neutrino understanding, atmospheric neutrino understanding, final understanding of neutrino oscillations in the 20-30 years up to 2010 with the discovery of the last angle, which is θ13. Neutrino astronomy began in 2015, and now we have the present with the next generation CP violating experiment and so on. CNO neutrinos from the sun in 220. This is what we know and what we don't know. We know neutrinos are at least 3, probably certainly no more than 3 coupled to the Z. We are assuming a 3 neutrino scenario for the moment. To answer the question made before, the mixing matrix is made of these 3 pieces with the 3 angles that are relatively well known. θ23 is close to 45 degrees, which is the maximum. It's consistent with 45 degrees. We don't know if it is a little less or a little more, what is called the octant problem, because some effects depend on the fact that you are slightly above or slightly below 45 degrees, but I will not cover that much. Typically, to study this effect between the second and the third family, you need, because of the delta m square, which is 2 × 10⁻³ electron volt square, you need either distance of hundreds of kilometers at MeV scale, or even more if you go to GeV scale. So typically you study this with the 200 kilometers up to 1,000 kilometers, or you use atmospheric neutrinos, which can fly a few kilometers if they are coming from above, up to several thousand kilometers if they are coming from below. You have the coupling between the first and the second family. In this case, it's θ12. The typical way to do it historically was solar neutrinos, but you can also use reactors. In that case, the energy is much lower and the distance must be of the order of 200 kilometers. Again, you can make the exercise to understand these numbers from the corresponding delta m square. and the formula I have mentioned before. And then you have θ13, which is the coupling, direct coupling between the first and the third, which is not that small. That is the main difference with respect to quarks. This coupling for the quarks is super small, coupling of 1 to 3. This makes CP violation in the quark sector very low, because a CP violation is proportional to all three angles. So if the if one of the angles is 0, you cannot have any CP violation. You need the three angles different from 0, and the larger they are, the bigger is the CP violating effect. The CP violation in oscillation is driven only by the so-called Dirac phase, or the delta D that is here. There are other two phases that come if and only if neutrinos are Majorana, and they are diagonal, so they do not contribute to the oscillation, but they do contribute to some processes, chiefly neutrino-less double beta decay, and I will mention in a moment. We know the mass difference between the elements, because the mass difference between M1 and M2 is this one, and M2 and M3 is that one. Let me go back to the notation. 1 and 2, because I should have stressed before, but I do it now. Now it's important that we realize that flavor against states and mass against states are not the same. In previous slides, I avoided to stress this, but now we have to do it. Once oscillations are discovered and once the mass term is introduced, quantum mechanically, either you observe the mass or you observe this flavor. You cannot observe both because they are incompatible in the sense of the Heisenberg principle. So normally, if you speak about mass, you should correctly say what is the mass of M1, of M2, and M3, and not the mass of electron neutrino, mu1 neutrino, or tau neutrinos. But you can give meaning to these masses, and we will see later. But rigorously, the mass-defined states are M1, M2, and M3. That's why you will normally say that the electron, the muon, and the tau neutrinos states are a mixture of the corresponding mass against states, or the other way around. By definition, M1 is smaller than M2 by convention. So you assume that M1 and M2 are the two states that correspond to solar oscillation. Then you have the third. The third, you see this delta M square is much bigger than this one. That's why usually this is called small delta M and this is big delta M, because there is a factor 20 between the two. There are two mass scales essentially. But oscillations measure only the absolute value, not the value. So you don't know the sign of, by definition, this is positive, because by definition you put M1 below M2. But then you don't know where to put M3, and this is so-called ordering problem. It used to be called the hierarchy problem, but now hierarchy is not anymore fashionable. People say it's an ordering problem, because actually it's not a hierarchy, it's just an ordering. You have to decide if M3 is above or below. Actually, nature has to decide. We don't know yet, because oscillations are not sensitive to first order to this. You can be sensitive to this, but you need a very precise measurement, studying very carefully either mass propagation or very high precision measurements. We will come to that slightly later, but today we don't know if M3 is lighter or heavier than M2. Take into account that these are differences. There is no vertical scale, because we don't know the mass. You can move these three numbers up and down between 0 and essentially 1 electron volt, because of the comment I made before. You cannot go above 1 electron volt with the electron neutrino mass, the one that you measure from the kinematic of the beta decay, but essentially the scale is unknown. The other parameter that is not known is the Dirac phase, which there are hints that is relatively large, but still with very large error. So essentially, we don't know yet what is the size of CP violation in the neutrino sector, and we have no information whatsoever of alpha 1 and alpha 2, which can be measured only if neutrino less double beta decay are measured for several nuclei. We will see later. So this is the list. I try to go quickly a little bit. The list of things we don't know yet about neutrino. Many things about neutrinos we don't know. So it's still a very active field of research. We lack information about the parameters. We don't know the mass scale. We are still beginning the astrophysics with neutrino, but we are really at the beginning. We still need to detect the cosmic neutrino background. We don't know about supernova neutrinos, except one event in 1987, which is super famous, but it's the only one. We still lack a lot of information about the neutrino supernova. So now I go to the sources. To do an experiment, you need a neutrino source. You need an abundant neutrino source for the reason I told you. Neutrino detectors are massive, but the mass you can build is limited by cost, by space, by technical feasibility. So you need huge fluxes, and the sources that can be used are not so many, although not so few either. There are artificial ones, nuclear reactors, accelerators are the most important. In very specific cases, not easy to implement radioactive sources. And then there are natural sources, the sun, atmospheric neutrino coming from a faraway location in the space, so-called cosmic neutrinos, geoneutrinos coming from the radioactivity of the Earth. There is the so-called diffuse supernova background, which is not a single supernova nearby, but the statistical convolution of all supernova happened around our location in the universe in the last eras. You can have individual supernova neutrinos if it is not too far, and then the beautiful dream of detecting the neutrinos from the Big Bang, which are called the relic neutrinos. Reactor, neutrino sources. This is the plot of natural neutrino sources. Well, actually, they include some non-natural one, but if you are in a specific location and you measure the flux of neutrinos as a function of the energy, first of all, notice that neutrino energies span a huge interval from 10 to the minus 6 up to 10 to the 18 electron volts. So it's a beautiful 24 orders of magnitude range. At very low energy, super low, you see, well below the electron volt, you have the CMB, the cosmic neutrino background, are produced during the Big Bang, is the first second, then they decouple, they are still there. They are like the CMB of photons, but they are neutrinos. They are expected to be about 400 per cubic centimeter in every cubic centimeter of the universe. But they are super low energy and they damn hard to detect. So far, we don't have a technology to do that. There are ideas which I will not cover, but they are really a dream. Some of you maybe will discover CMB, but not today, and even not tomorrow. It's going to be a long trip. Beside the CMB, there are solar neutrinos. The one that we studied are the one from nuclear reaction. There is actually a component from thermal, which is due essentially to neutrino bremsstrahlung in the sun. It's not small amount, but it's still low energy. You see, these are electron volts. So these are neutrinos that would be in the range below 1 keV. Detecting 1 keV neutrinos is too hard because, as you see, the cross-section goes with energy. So when you convolve the energy and you put the flux times energy, which means the cross-section, you see that the thermal part has a flux that is really too low to be detected with existing technology. The one that can be detected are the solar neutrinos coming from nuclear reactions, which are In the MeV range, or a little bit below the MeV range, you can go down to 100 keV. Borexino started from essentially 200 keV up to a few MeV. Other experiments have measured around the 5, 6, or 7 MeV, but this is the region in which you can detect solar neutrinos. Then you have reactors that pollute the natural sources because there are many reactors around the world. Then there are the geoneutrinos, the neutrinos coming from the radioactivity of the planet. And then you start getting the neutrinos from the atmospheric neutrinos, which are the secondary neutrinos produced by collisions of protons into the atmosphere. And then eventually you get the purely cosmogenic flux, the neutrinos coming from space. You see the flux is going down with the energy increasing, going down a lot. So the more is the energy, the more you have to increase the mass. Although the cross-section is increasing with the energy, the flux is going down faster. So you see from here, flux times energy, it goes down very fast. So if you want to detect these neutrinos, you need a cubic kilometer of detector, which is ice cube. If you want atmospheric neutrino, you need at least 10 to 100 kiloton of detector. And this is Super Kamiokande and other detectors. And then when you go here, you can live with 100 ton, 1 kiloton, 10 kiloton, depend on the precision you want. We don't have a technology to study neutrinos here today. This is a kind of the same plot, but I use it to stress another fact. Typically, neutrinos can cross matter very easily. So we keep saying that even a planet is transparent to neutrinos. This is mostly true, but not completely true at the highest energy. This is a function of the energy. This is the cross-section. At around 10 to the 15 electron volt, 1 PeV, you start to have a center of mass energy that is close to the W mass. This peak is the same as the Z peak we considered 2 hours ago at lab. That was due to the Z mass, but at some point your center of mass energy is close to the W mass, and when it's close to the W mass, the cross-section goes up very high. If you do the calculation of the mean free path at the peak, it gets much smaller, so the Earth is not anymore transparent here. But look, this is a logarithmic scale with very fine cuts. So you see that already here, the mean free path is close to the Earth diameter. So it's just this region in which the transparency is not there. Let's say below 1 TeV or even 10 TeV, the transparency is still there. So you can look at atmospheric neutrinos from below or from above. That's the point. When you look at atmospheric neutrinos, can I look neutrinos down, coming from the other side of the Earth? The answer is yes, until, let's say, 10 to the 13 or something, maybe 10 to the 14. And then the answer is no, the Earth is not anymore transparent. If you want to do astronomy at 10 to the 16 or 10 to the 17, you better look up. This is an important slide to understand the neutrino detection in a general sense. Suppose you have a detector and suppose you have a flux. In a very general sense. So this formula is usable essentially in all cases. The number of events you observe is the number of targets you have, the amount of patients you have to take data, the time. You will depend on your detecting threshold, very important. Usually your detector, you will not see neutrino starting from 0. You need some minimum energy. This number can be very low with some technologies, but is essentially never 0. Up to the limit in which you have a flux, then you have your flux, function of the energy, you have a cross-section, you have a detection efficiency, you sum over all energies, and this is the number of events you get. neutrino events are always fixed target. We don't make a neutrino collider. It's not unthinkable. Maybe in the far future, we could have two neutrino beams crossing together and use it, but do the calculation, the intensity you need is ridiculously large, and there is no more. So today, the only reasonable experiment is an experiment in which you have a neutrino flux against a piece of matter, which is your detector. The parameters I already mentioned, if you put typical numbers, you understand the scale of the neutrino experiments. I made two examples, but you can easily use this formula to do other simple calculation. In case of solar neutrinos, for example, if you count the number of electrons in 100 tons of materials, you get this number. This is the number of seconds in a day. This is an example of beryllium-7 neutrinos, which is 6×10⁹ square centimeter, just to give an example. This is the cross-section at the right energy, and you get about 50 events per day. So in 100 tons of detector, the typical rate you get is 50 events per day. If you will get a class on statistics, so you will be able to understand, I'm sure you already are, but with this kind of events rate, usually the statistical error is relevant. Getting sub% precision already is hard because you have to go to 10,000 events with zero background, which is something that it's not easy to do, including systematic. It's usually unlikely to get sub% precisions. Another example is an accelerator, in which, and this is an example I took from a typical target in liquid argon. Again, this is the number of nucleons per kilogram scaled with the mass. In this case, I put a year and not a day for reasons that will be clear. What is the flux you can imagine? Well, at 1,000 kilometers from the accelerator, if you get of the order of 1 neutrino per square centimeter per second, it means you already have a good beam. You have an efficiency that, okay, you try to keep it as close as much to 1, but never exceed 1. And then you have the cross-section again, using the formula shown before. Calculation is this level. This is a 10⁻⁶. So if you hope to have events per year, you immediately understand you need a kiloton scale. Otherwise, you will never get it. Increasing the energy will help. So higher energy helps, but if you want to make an oscillation experiment, higher energy means more distance to get the same effect. But if you put more distance, you decrease the flux accordingly. So playing really with the energy is not straightforward that you can gain. The real gain is by increasing the mass. And for high precision accelerator experiment, the 10 kiloton scale or the several kiloton scale is the minimum. Some information about the sources, the nuclear reactors. I already said, so I go quickly, but the nuclear reactor is a beautiful neutrino source. The typical numbers are this one, 2×10⁻20 neutrinos per second per gigawatt thermal power. A typical core of energy production is 1 gigawatt. Some sites have 4, 6, 8 cores, so you can get about a factor 5 or 10, in some cases more than this in neutrinos. The typical energy is half an eV. They come from fission. Reactor is a beautiful source for neutrino experiment, but it's a hard source for high precision neutrino experiment. Why this? Because predicting the flux of neutrinos is not easy. There is a lot of complexity in the fission of uranium and thorium, particularly in this case of uranium. Uranium will fix in 2 fragments, and you can ask yourself what neutrinos I am getting. The answer is a super complex Answer: because you get neutrinos from hundreds of different nuclear reactions. You are not getting just neutrinos from the main radioactive chain decays. You get neutrinos from many intermediate isotopes that beta decay during the life of the reactor, and your flux is a convolution of literally hundreds of thousands of different processes. So predicting the neutrino flux is hard, and reactors are beautiful. For example, the Juno experiment is about to start a beautiful measurement about mass ordering using a reactor, but there is a big investment in understanding the reactor, and there will be a dedicated close detector, the so-called near detector, to measure the exact flux, because if you just rely on the prediction, your error becomes large. About 20 years ago, beautiful experiment was done in Japan with reactors, which was the Kamland experiment I mentioned, because it was a beautiful oscillation experiment with the benefit from the fact that the Kamioka mine is located at the center of a ring of reactors whose typical distance from Kamioka is about 180 kilometers, which is about perfect to study neutrino oscillations of the theta 1,2. Okay, this angle is theta 1,2. This is the disappearance formula for electron neutrinos emitted by the reactor. Delta m square is of the order of 10 to the minus 5. The energy is about of the order of MeV. So you need typically 100 kilometers to get a good effect. This was done in the years 222 to 203. It was made of a large balloon of liquid scintillators using Rhine's-Cohen inverse beta decay. So in that case, the detector was a sphere of photomultipliers with a large balloon containing the liquid scintillator, and the result was this beautiful measurement in which you measure how you do this plot. You remember the Rhine's-Cohen prompt and delayed technique. The prompt event has an energy that is proportional to the neutrino energy. So with the Rhine's-Cohen technique, you can measure, infer, let me say, the neutrino energy. So you know the distance, you know the energy, so you can plot the number of events as a function of L over E. L over E is this one, this is the L, this is the E. This is known, and you can extract from the fit the delta m square very precisely, because the delta m square controls the distance of these two peaks. This is the first experiment in which the word oscillations take a meaning, because it's really oscillation. It's oscillation of the probability as a function of the distance. This is correct, and the Kamland proved beyond any reasonable doubt. It was already proved by the Snow experiment 1 year ago, but this was a very nice confirmation. I mentioned because in this case, the experiment was able to show the oscillation pattern very neatly. You see that the second peak is smaller than the first one, and the third is not very much visible. This is due to loss of flux, but also loss of coherence. As I said before, the more you increase L over E, the more the coherence is lost. That was an example of reactors. Now we go to beams. Another important artificial source of neutrinos are the beams. The beams are an evolution of the old idea of Steinberger, Schwarz, and Lederman, which is you take a proton accelerator. You want proton because you want pion. If you want pion, you need atom interaction, so you take proton. You don't take electrons. It would make no sense to use electrons. You use proton, you use a target. You try to focus the pion as the best you can. You're using quartz, so we'll see the design and some details. Then you have possibly a vacuum pipe. It's not easy to make a vacuum pipe because the pipe is very long. So you make a pipe as you fill it with helium if you are rich. You live with air if you are not rich. But of course, you have to allow the pipe to decay and not interact before. That's why ideally you would like a vacuum pipe. But it's never a vacuum pipe because it's too big and too long. Then from the pion decay, you get a new one that you could, for example, detect to monitor your beam, and then you have the neutrinos going. Then you have typically a near detector to characterize the beam, and then a far detector to measure oscillation. Again, if you want to make a high precision, you want to have the near detector because even predicting very precisely the beam intensity is not easy, and it's even less easy to predict the flavor content of this beam. There are difficulties that I will show later. So the highest precision approach is to have a near detector in which you measure very well the energy spectrum and the flavor content of the beam, and in the far detector, you try to identify the oscillation pattern. Three, please.
Which material will you be in the beam down?
It doesn't really matter in the sense that you will get a lot of pions from any material. What drives you the technology is that if you put a beam into a small target, you make an immense amount of heat. So the target is driven by technology. You have to find something that does not evaporate, is not destroyed by the beam. So some materials are okay, some other materials are not okay, but it does not really depend on the physics. It depends on the technology, on the thermal properties of the target. I will comment a little later on the targets. There were, stop me if you want, of course. Historically, there have been several beams, but let me comment on the most important recent one. The CERN to Gran Sasso beam, CNGS, which does not exist anymore. It was operated from about 2005 and 2015, and it was a beam from CERN to Gran Sasso. We will see some experiments made there. There is still an operating beam at Fermilab that send essentially the neutrinos to two locations, both in Minnesota. One is the Minos experiment, the other one is the Numi experiment. In the future, this beam will be sent, variation of this beam, not exactly this one, will be sent to Dune and in South Dakota, and is currently also using at Fermilab in so-called short baseline experiment that I will not call. And then the third, very important, is the one from the Keck laboratory in Japan. So from the J-Park site, there used to be a beam to Kamiokande experiment. Now it's to Super Kamiokande. In the future, it will be to Hyper Kamiokande, but it's still a similar program. In all cases, you have protons, 400 GeV at CERN, 120 GeV at Fermilab, 12 GeV in Japan. So the energy is different, which means that the optimal distance between the sites is not the same. You typically have, you had the 700 kilometers at CERN. You have about 700 kilometers from Fermilab to Minos and Numi. We will have about 1,300 kilometers in Dune, while in Japan, being the energy lower, the optimal distance is smaller, so it's about 250 kilometers, and this is the best distance. By the way, of course, moving Kamiokande would not be easy, so you don't tune the distance, but you tune the energy. So you have to build the right accelerator, taking into account that changing the geography is harder than changing the energy beam.
That's a question.
Please.
So, all the decay tubes are varying length. They're all quite different.
Sorry. Yeah. The decay tubes are tuned. What in principle an infinite tube is right, in the sense that you want all pions to decay. in principle. But you are a real person in a real planet with a real budget, by the way. So what you do, you have to make it as long as possible without wasting money. What does it mean? It's an exponential decay. If you have a 3 decay length, you will have essentially all pions, and any additional length will cost you linearly, but will add very little. So if I have to say, typically the length of the decay tunnel will be enough to let 90% of the pion, 95% of the pion to decay. The additional length that you may add to get the another 5% would be too expensive. Okay, but it's a practical point. It's not a theoretical one. If it is too short, you don't have enough intensity. If it is too long, it becomes too expensive and you are not funded.
Yeah, basically, Marco for many years has been the president of the Einstein Astroparticle Committee, so that's why this kind of answers are relevant ones.
So in this target, do you have some selector to select the pion negative and positive?
Yeah, I come to that. The target, no. The magnets after the target select the parts. So few pictures to answer your question. The complexity of the target. The target is a hard device to build. Why this? Because of the power. Typical beams have powers of the order of 100 kilowatts to several hundred kilowatts, and the next generation we dream about megawatt. Do the calculation of what is the temperature increase of a cubic centimeter of any matter if you put 1 megawatt of power into a cubic centimeter. Okay, you immediately understand that it will be vaporized in seconds or in tens of seconds. To avoid that, you have to cool it down. There is a lot of technology to find the right material that allow you to be resistant. One problem. I don't want to be too technological, but the target must be resistant, but by also something that does not activate too much. If you put a lot of protons and the material you have put around the target are such that after 1 year of data taking, that target becomes radioprotectionally impossible to manage, you have a problem. Because if you have to replace it, who will go there to replace it? If nobody can go there because nobody will be willing to die for you, you need a robotic system. And the robotic system is a lot of money, and nobody will be happy to give you such an amount of money if it is not absolutely necessary. So you have to design the target so that it's feasible, it's maintainable, can be replaced. It's a lot of technology. Your question. After the target, you want to select the momentum. You wanted to select the charge, and that's easy, but it's very important because if you select either plus or minus particle, you select neutrinos or antineutrinos. But then you want to focus. Typically use 1 or 2, sometimes 3 horns. Again, I don't want to be too technological. I don't enter the details on how it's done, but the geometry of the magnetic field is such that you start from a diverging beam to a somewhat focused beam. This is ideal. You never get all the pions absolutely parallel out of the second horn, but that is the concept. Sometimes there are 3 horns. Typically, one of the magnet can be reversed, so you can, if you select pi plus, you get the neutrinos. If you select pi minus, you get antineutrinos. As I said, you don't get a pure mu neutrino beam because the pions will decay as they want, and also the kaons will be there. So eventually you get a beam that is at the level of 10 to the minus 3 pure. If you go to 10 to the minus 4, you get contamination of electron type, of antineutrino type, of all kinds. These are design of horns. For you see the complexity of the technology, and this is the horn seen from the side. You need a very careful geometrical design in order to get the best focus. One important kinematic trick, in the center of mass frame, the pion will emit a monochromatic neutrino. If you boost, you get that this is the relation between the momentum of the neutrino in the lab and the angle. This means that if you go off axis, so instead of putting your detector along the line of the beam, you go at an angle, you gain. You gain in the sense that you lose flux, you lose neutrinos, because most of the neutrinos go into the forward direction. So you lose intensity, but you get a narrower beam. You see this plot, this is the black plot on axis. So this is what you will get staying on axis. If you go at 7 millirad, 14 millirad, 21 millirad, the flux decreases, but the energy distribution gets narrow. Of course, what is the right thing to do? Depends on what you want to do. If your measurement is benefiting from intensity, you stay on axis. But if you want to measure neutrino oscillations, it might be that going on off axis is better, because the amount of neutrinos in the right energy range could be higher. So suppose you want to make an experiment in which the optimal oscillation energy is 2 GeV. You pick the black or you pick the red? You pick the red, although even if the flux of the red is much smaller than the flux of the black. The reason is that, yes, you have a lot of neutrinos, but with the wrong energy to study oscillations in that particular regime. So it's a kind of optimization. Sometimes experiments are on axis, sometimes are off axis. In the case of Dune, the near detector will be movable, so we'll stay on axis and off axis to benefit from both cases. An example of a detector at Gran Sasso on neutrino beam was the Opera detector, who studied tau neutrinos. I am not giving details about Opera, but this was the first experiment to detect the appearance of tau neutrinos from mu1 neutrinos. It was made in the years around 2010. It collected about 15 beautiful tau neutrino candidates appeared in this CERN Gran Sasso beam. I skip the technology again. Another experiment at Gran Sasso, on which I will spend a little bit more time because it will also be the future of the Dune detector, is the liquid argon technology. The liquid argon technology has an advantage in the sense that you can build a large volume of liquid argon. In principle, you can make a very massive detector. Liquid argon is the electric medium, so you can collect charge by ionization of charged particle, but it's also a scintillator, so you can collect light. So you can trigger on the light, you can get an information about the event into the argon from the light, and you can measure the tracks, the energy, and many features of the event from the charge. The technology was developed by INFN in the 90s. It became the Icarus detector in 2010 at Gran Sasso, and it's now the base of the future liquid argon technology. I will not cover that. I assume somebody else will do it, but a similar concept with some change, the TPC concept together with the dual phase technology has become also the base of many dark matter experiments with xenon and with liquid argon. So it all came out from this effort.
Juliana will cover it.
Okay. Of course, you can measure the charge in many points. So if you have a track in the argon, you can reconstruct the track very precisely as a function of time. So you have a multiple measurement of the index, you have multiple measurement of the position. You reconstruct in 3 dimensions the event very neatly, as it is shown here. For example, this is an example of a kaon decaying to muon decaying to an electron. You see beautifully the tracks. This is possible only with liquid argon technology. It has the capability to give details of an event that in principle are really immense. Let me say in principle, because it will have still work to be done to show that this is really beneficial, because the technology is very complex, where people is still working on the development of reconstruction of the capability to really benefit from this amount of information, but it's clearly extremely promising and extremely interesting. This is an example of a beautiful event in which you have an electron neutrino scattering off a proton. So you have a quasi-elastic event in which you have a proton coming out, and this is an electromagnetic shower. You have never seen an electromagnetic shower in this detail. Of course, you can also imagine that doing automatic reconstruction with computer-aided software, it's damn hard. Artificial intelligence, of course, is now very fashionable, but it will be certainly the base of the reconstruction of these events. Work is in progress at Fermilab on both the Icarus detector that now is at Fermilab, but also in the future in the Dune detector, and I'm sure there will be fantastic results. The same technology will be scaled up. Icarus was a 600-ton detector. It will become 2 modules of 10,000 tons detector, fiducial volume at Dune. There will be 2 technologies. One will use the so-called horizontal drift, in which you have wires in the lateral part, and the charge drift horizontally, why the name. And this is the same concept of Icarus. The new technology, which is also motivated from dark matter experiment, is to have the drift vertical and have detector on top of the detector. This is a detail. We will see what of the 2 will work better. The 2 Dune modules will be done with both technologies, and the best will decide what will be the third. Let me just summarize what I said with a formula. Usually, understanding the neutrino source, either with the reactor or with beam, is not easy. You don't have an a priori knowledge of the source. So you want to measure the source very well, and typically what you do is to put a near detector close to the source before oscillations get relevant. This formula, don't spend too much time here. You will have time to think about it, but this is essentially the idea. You have at the far detector, you have the effect of the oscillations, which is this part. And in the near detector, you don't have this part, but you also have you have only the dependence on the cross section, on the flux, and on the detector components. In principle, you may dream that this red, green, and pink part cancel. It's not true. They don't really cancel, but the effect is diminished. So you gain by having the near detector, but it takes a lot of work to disentangle the effects. I'm not entering into the details, but this is the future. To learn how to make this formula work is the main purpose of the next generation experiment. Because if you want high precisions, you do need to have a full understanding of the beam, and this is a key point. Let me just summarize the formula and summarize what will be the sensitivity to CP violation of Dune here. I leave you as a reference. So these are the official plots of what will be the sensitivity of Dune, and to be politically correct, let me also add the very same sensitivity foreseen for hypertonic candle, which will be, let me say, a complementary experiment, very important, because it will have several advantages and also, in my opinion, some less convincing elements. The advantages is that will be a more stable and more known technologies. It will be a water detector technology, 20 times bigger sorry, 8 times bigger than Super Kanyokande, so it will have a huge statistics. It is a very well understood technology with very simple neutrino detection capability. They already got 2 Nobel Prizes, so they know how to do the job, and this is very clear. They will have a lower energy beam, which will make a little problem in the sense that they will not be able to disentangle the effect of neutrino propagation in matter and the CP violating effects. They will have to rely on an independent measurement. But let me say that I think it's very wise and very correct that the community is doing both, because 2 independent technologies, 2 independent beams, 2 independent collaboration, studying a very important and very difficult science problem. So I think it was the right thing to do, that globally the world community has concentrated the effort on these 2 approaches, which in my opinion will be extremely successful in both cases and will provide important information. Very likely, almost for sure, Hyper-K will begin earlier because the schedule is shorter. They plan to start the data taking in 27, 28, and it's very likely that they will keep it. Dune will arrive a few years later, so it's easy to predict that probably the first measurement will be made by Hyper-K. Probably in the very long run, it might be that Dune will get the highest precision, but we will see what will happen in the future. I changed topic and I switched to another important topic, not related to oscillations, but related to coherent elastic scattering. Coherent elastic scattering is the scattering of a neutrino with a nuclei elastically. It was considered an extremely difficult measurement, and it is. In this case, the difficulty is on the fact that neutrinos are very light, nuclei are very heavy. When a neutrino hits a nucleus, the kinetic energy transferred to the nucleus is very small. So you get a very low energy nuclei that is very hard to measure. In order to measure it, you need a very neat experiment with very sensitive detectors. The final idea was successful at Oak Ridge Lab in the United States, in which the neutrinos produced were obtained by stopping muons stopping pion into a material in which you have essentially a monochromatic neutrino of about 50 MeV. These neutrinos hit a nucleo. The cross section is this one. It depends on the nuclear number of nucleons squared, because it's called coherent scattering, because the neutrino interacts altogether with all nucleons in the nuclei. So it is the amplitude that is proportional to the number of nucleus, and the cross section gets a square. So the cross section grows quadratically with the mass of the nucleus. This would tell you, well, so the largest mass is the better. Yes, but if you take a large mass, the energy of the recoil gets smaller. So life is never easy. Actually, the most successful are nuclei somewhere in between. So not so light, but not so heavy. I'm not covering the details, but let me say it's a beautiful experiment made at Oak Ridge with the REACH program, because they plan to measure several nuclei. The idea is the following: they have the proton, they produce pion, they have a stopping pion, and they get either the decay at rest of the pion or the decay at rest of the muon. Of course, if you get the decay at rest of the pion, you have a monochromatic neutrino. If you get the decay at rest of the muon, you have 2 neutrinos, but they are not monochromatic. But of course, it is interesting to study both. They use a proton beam to produce the pions. This is in Oak Ridge in Tennessee, United States. I'm not giving you too much details, just to tell you that they successfully measured the coherent scattering of several nuclei. They started from cesium iodide and liquid argon, and they successfully got clear and unambiguous signal. And they recently announced that they measured also on germanium. The selection of the elements is also driven by technology, because yes, I want to study lead, but what kind of detector I can do with lead that can have such a low energy, because the amount of energy you get from the nuclei is hundreds of electron volts or not much more. You need a detector that is capable to detect this energy. So it depends on the technology. You use a cesium iodide crystals and you can measure the scattering on cesium and iodide, or you can use a liquid argon detector, or you can use a germanium crystals, and so on. So the selection of the nuclei is also driven by the technology. Let me go quickly now to solar neutrinos without spending too much time, but of course the sun is a powerful source. It used to be an unknown source because the knowledge about the exact functioning of the sun came together with the first experiments on solar neutrinos. So theory and experiment evolved together. The person who made that happen was John Becquerel, who really made the real job to understand the sun in detail. The basic understanding was done before by Hans Bethe, by Fowler, and by others. But going to the details at percent level, which is what you need to understand the solar neutrino flux, is a job made by John over decades. And he developed the so-called standard solar model, which is a theory that is able to predict in detail what is the solar flux of neutrinos of any component of any energy. You see a measurement of the precision achieved from the beginning, in which all errors were very large or huge, up to high precision physics that we now have on PP neutrinos, on bottom-8 neutrinos, or on CNO neutrinos. The sun works through two chains. One is the so-called PP chain, which I assume it's rather well known. Maybe slightly less known is the CNO cycle, which is a list of reactions driven by carbon, nitrogen, and oxygen in the sun. In all cases, what you get is about 2 neutrinos per helium nucleus. The typical energy released is 25 MeV, and the typical energy of neutrinos is half an MeV. This is the predicted spectrum. We know very well, thanks to the work of John and his pupils. Let me say this is the latest, or one of the latest release of the expected solar neutrino spectrum from the sun. Very quickly, because this is history, but the first measurement came using the so-called radiochemical approach, in which you absorb a neutrino in a chlorine atom and you count the argon-37 atoms using the fact that the argon-37 is itself radioactive, so you can count in a detector. Roy Davis spent all his life detecting solar neutrinos this way, reaching this beautiful precision at the end. And you look at the dates. If there is a person who deserved the Nobel Prize, is Ray, because he's really spent his whole life doing this measurement very carefully and very neatly. The result was completely inconsistent with the solar model, and this was one of the evidence of oscillations, as you all know. Same thing was done by gallium atoms in Gran Sasso and by SAGE experiment in Russia, two activities, GALEX, which became later GNO at Gran Sasso, and SAGE, which is still active in Baksam in Russia. In this case, you have a gallium-71 as a target. The concept is similar. You count the germanium atoms you produce and you measure the neutrinos. Again, the deficit was observed, confirming the solar neutrino model. This is the measurement of Gallex compared to the prediction, which is absolutely not compatible. Another technique to study solar neutrinos, of course, is water. You can detect solar neutrinos on scattering on electrons in water, and this is the big, fantastic effort made first by the Kamiokande experiment and later by the Super Kamiokande experiment. This is the basic physics. When you get a neutrino hitting an electron, you get light. The light is emitted in a cone that is a function of the beta, but also the range of the electron is proportional to the energy. So the total amount of light is proportional to the energies. The number you care about being an experimentalist is this: about 400 photons per centimeter of track in water in the visible or near ultraviolet region. This number is small, but not too small. So if you have a reasonable acceptance, and 1 centimeter, how much it is? 1 centimeter is a few MeV energy because the range of an electron is there, and you get the signal from a solar neutrino. This is some details of the technology used. Slide shown by Nobel Prize Takaaki Kajita, showing the concept of how you detect the solar neutrinos, or also atmospheric neutrinos, but in this case, particularly the solar neutrinos using water. Note that Super Kamiokande also benefited from an important R&D on the development of very large tubes, which of course are very important to collect a lot of light in a very large volume. This is the very well-known picture of the Super Kamiokande detector with all the photomultipliers while the water was raising, and you see this fantastic detector. Again, without going too much details, one important thing about water compared to other techniques is that with water you can also measure the direction of the incoming neutrino, because you measure the direction of the electron through the position of the light in the cone. So you can reconstruct the energy of the electron, but also its incoming direction, and being the direction of the electron related to the direction of the neutrino, you measure the direction of the neutrino. The plot shown here is made by Super Kamiokande, was published in 2016 with some important statistics, and you see clearly that if you plot the distribution of events as a function of the direction with respect to the sun, there is a beautiful, nice peak in the direction of the sun that shows that you see neutrinos coming from the sun. You cannot do it with liquid scintillator. You cannot do it with radiochemical techniques. That's why I insist on this. I am not covering the experiment. I'm not showing you the result of the different experiment in detail. This can be done by somebody else. I want to stress the feature, the advantage and the disadvantage of the various techniques. This is the measurement made by Super Kamiokande and Kamland on θ12. Of course, water was used also to study in detail the atmospheric neutrinos. Again, I'm not covering the subject in detail, but of course you can study very well neutrinos from above, from below, disentangle muon neutrinos and the tau neutrinos. This is the super famous slide shown by Takaaki Kajita in 1998, proving historically the detection of an asymmetry between upgoing and downgoing muon and electron neutrino consistent at 6.2 sigma with the neutrino oscillations of atmospheric neutrinos. Water can be used also if solid. There is not really much difference in the sense that light propagates in ice as well, and you get a large amount of light, even in ice if you are deep enough, because you see, the ice on top is not transparent at all, but it becomes very transparent when it is deep at high pressure. And if you go deep enough in the ice, you can put photomultipliers. And if you are clever enough to put enough photomultipliers, you collect Cherenkov light from muon crossing the ice. Why doing so? It's not easy to go to South Pole, but if you want to make a detector that is 1 kilometer cube in volume, you cannot build an artificial detector. Super K is 50 kiloton, if I'm not mistaken. Hyper K will be 8 times more, 400 kiloton. But you will never be able to make a gigaton with a tank. You better use natural sources, and the natural sources you can use are either ice or water, if you go deep in the sea or in a lake, or if you use the atmosphere. This is a future dream from space. The technique that works so far is the ice, with the ice cube experiment, which I assume you already heard. Ice cube detected several non-atmospheric super high energy neutrinos from the cosmos using these techniques. So studying either the crossing of muons in the ice or the development of shower in the ice, upgoing or downgoing. In all cases, the concept is the very same as Super K. You have Cherenkov light emission into the ice, you have photomultiplier tubes dispersed into the ice that collect the light and gives you information about crossing muons and therefore crossing neutrinos.
How deep is it?
Ice cube is from about 2,000 to 3,000 meters, if I'm not mistaken. You have to go deep because you wanted to use the top layer as a shield against cosmic rays. So you have to go deep enough not to see the many muons from above. You still see some muons from above, but you want it to be shielded, so you go deep. But of course, you don't want to go too deep because you get too close to the rock, and that is not good because the ice is not very clean. So the optimal, I go by memory, but I think that the detector is roughly between 2,000 and 3,000 meters, or maybe 1,500 and 2,000 and 2,500, something like that. There is at least a kilometer and a half of shielding above. And then there is 1 kilometer of detector.
When the rocks start?
I think depends on the location, but I think that the total depth of the ice is something like 3.5 kilometers or something. And then you have the rock of the Antarctic. I just mentioned, because it's beautiful, at last Neutrino conference, there was the first detection of a super high energy neutrino events in water. This is the kilometer cube net detector. It's an underwater in Sicily. There are, again, like in ice cube, PMTs dispersed in water, in this case floating. And there was a beautiful event of immense energy. It is this event here, which corresponded to about 100 PV and is the highest energy event ever detected as a neutrino. What do you learn from this? Not much, except that they do exist. So this is a proof that the super high energy neutrinos coming from space exist. This event is much more energetic than the highest energetic event detected by IceCube. So it's very interesting by itself. It's just one, so there is not much that can be inferred from a single event, but let me say it's the beginning probably of a new field of research. Let me skip snow. The snow was not because it's not important, but I assume it's more known than others. It is the experiment that proved that solar neutrinos oscillate along their trip. From the technical point of view, the important thing to stress about SNO is that they use the deuterium as a target. What is good about deuterium? That you can break the deuterium and make a charge or current interaction and have two proton and a positron, and you have, in this case, you are sensitive only to electron neutrinos. You can break the deuterium, making a proton and a neutron, and in this case, you are sensitive to all neutrino types. And then you can also make an elastic scattering, and you are sensitive in a different way to all neutrino types. Putting this information together, SNO was able to prove that neutrinos do oscillate, that the neutrinos coming from the sun are not only electron neutrinos, but you also get some muon and tau neutrinos that explain why the other experiment, which are not sensitive to muon and tau neutrinos, saw a deficit.
Just the type, of course, it's an electron, it's not a positron.
Of course. Thank you. It's interesting. I never noticed it. I gave this lecture several times, but no, I know you are absolutely right. There is a no.
There is a question over there.
Yes.
Right, it's probably a really, really stupid question. But can you go back to the slide with, sorry, the scriptlers, guys. Sorry, but the one
Which
with
one?
the one you were just on with the equation.
This one?
One before that. So the
This
charge-
one?
yeah, that one. So the charge current reactions, you've got an electron neutrino and a deuteron producing two protons and an electron.
This is an electron.
Yeah,
Yes.
yeah. So at one point in this talk, I think the last session, you mentioned that you can't ever know if it's an electron neutrino or something. I know you can because it's got. So I'm confused about why can't you find out the energy from this equation? Why can't you find the mass from the energy from
No, which mass?
the mass of the neutrino?
No, you don't get the mass of the neutrinos.
So even though you can detect the protons in the
No, you prove with this technique, you prove that the neutrinos coming from the sun are not only electron neutrinos, because if you count electron neutrinos by this technique, and then you count the neutrinos by these techniques, the flux here is bigger than here.
and that's what it tells you.
But it's crucial,
Oh well,
because the total number of neutrinos is in agreement with John Bacall calculations, while this is not. But this is what a radiochemical experiment and also other, for example, Kanyokande experiment measured elastic scattering on electron. The elastic scattering is not the same. If you go back 2 hours, I've shown you the elastic scattering of electron neutrino to electron as a cross section that is bigger than the muon and tau neutrinos to electron. So if you don't know the flux and you count the events, you see a mismatch if you assume they are all electron neutrinos, because the numbers do not match. Of course, the problem is solved if you know that it's not really electron neutrinos, because the cross section is lower, so the flux must be bigger. And if you know to tell how many electrons, you can tell how many non-electrons, and you fix the problem.
okay.
So the independent measurement of electron neutrino and muon tau neutrinos was the key to pinpoint the fact that solar neutrinos at the origin are okay, but they do oscillate and they arrive on Earth when not anymore as a pure electron neutrino flux, but also as a mixture of electron neutrino plus muon neutrino plus tau neutrinos.
Thank you.
Okay. By the way, solar neutrinos arrive as a mixture. It's not coherent oscillations. The flux we get at first is completely non-coherent. It's just a mixture of electron neutrino plus muon neutrino plus tau neutrinos. Let me skip Borexino because it's my experiment, so nobody get offended, but I'm late. And let me, and you get it in the slide, and you will see there are some details on the radioactive background fighting in Borexino, which I think I can skip today because time is running, and I want to devote the last 10 minutes to some other topics. The first is supernova. We only got one supernova in 1987. Was a beautiful event detected by Kamiokande experiment. Ancora mezz'ora? I thought, okay, non alle 4, alle 4, okay. So I can go slower, good. Because so we need some time for questions. So the first event detected, the only one, unfortunately, is the supernova 1987A. Was beautifully detected by Kamiokande in Japan, by IMB detector in the United States, and by Baksan detector in Russia. It was a single supernova in the large Magellanic Cloud and in the small Magellanic Cloud, and as you can see, the supernova, the satellite star is barely visible in this plate, and it outshined the whole hosted galaxy during the explosion. We got about 12 actually, neutrino events from the supernova, which of course, in a burst that lasted about 10 seconds. It is immensely interesting to look at supernova neutrinos because supernova neutrinos are emitted by neutronization. I'm not covering that, but during the supernova explosion, the core of a star collapses. Protons and electrons essentially merge, form a neutron star, or possibly a black hole if the star is very heavy, but if the star is not very heavy, they form a neutron star. And during this process that is called neutronization, which is an immensely complex process, a huge, fantastically large amount of neutrinos is emitted. This number of neutrinos have to propagate through the neutron star matter. They contribute probably to the explosion, so they are part of the mechanism that make the star explode. They oscillate in a very peculiar way because the matter is so dense. I'm telling this to tell you that measuring supernova neutrinos would give an immense amount of information, both on neutron stars and on neutrino fields. So it is a super interesting event, unfortunately very rare. We don't know how many supernova explode in our galaxy, but it's probably statistically a few per century, but a few per century, if you are unlucky, could mean that you have to wait 50 or 60 or 80 years before you get another one. Question.
How far away the star actually was?
It was about 50 kiloparsec. This was, it's in the small Magellanic Cloud, which is a satellite. It's a small satellite of our galaxy, so it's not inside our galaxy, but compared to the sun, it's on the other side. So the distance is about 50 kiloparsec. So there are interesting programs that will come. The future will be to observe supernova neutrino burst in hyper-Kamiokande. It would be fantastic. The supernova was detected in Kamiokande, not super Kamiokande. Kamiokande was 1 kiloton. Hyper-K will be 400 times more. So it would give thousands, many thousands of events. It would get thousands of events in the small Magellanic Cloud, but if we get a supernova from the center of our galaxy, which is 5 times closer, they will get 70,000 events from the supernova, which means they will be able to perform very precise study of neutrino as a function of the energy, of the flavor as a function of the energy, disentangle the origin, so the mechanism that will produce. Look, you see, during the formation of these are milliseconds, okay? We cannot do anything with this data in 1987 because yes, we got some events, probably some of them belong to the first second or so, but the statistics is so low that you learn nothing. Suppose you have a huge statistics, which you will get eventually in hyper-K. Unless we are very unlucky, sooner or later we will get another supernova, and if we have hyper-K on when the supernova will arrive, it will be really beautiful. Because with these statistics, you can imagine to get many events in the first second, in the first half second. And the first half second is very interesting because it is the moment in which the neutrinos are forming during the neutron star collapse, but also propagating inside the neutron star. It takes several seconds for the neutrino to come out of the neutron star. So the early moments are very interesting. And to study the early moments in high precision will give beautiful information. The earliest part is very interesting. Then we will get events for many seconds after, as we did in 1987, but the very initial part with high precision will be fantastically interesting. The same we'll do with Dune. Dune can do something complementary. It is smaller, so the highest precision is expected in hyper-K, but the Dune will have the advantage to study very carefully the electron type because this event on argon is possible only for electron type neutrinos, so will give complementary information. So hopefully the supernova will happen in the galaxy when both detectors are on, and if this will happen, really, we could get a fantastic amount of information of an event that otherwise it's impossible to study. I have not stressed that because I assume is well understood, but neutrinos bring information that, of course, photon cannot bring. They come from deep nuclear processes, and you will never know how a supernova works with the photons. Yeah, you know that there is a lot of energy, that there is a lot of light, that they are very bright, but nothing will tell you about what make them explode and what is the exact mechanism that made them form the neutron star. Neutrinos can tell us a lot about it. Let me discuss the last 10 minutes, and then I leave some time for questions about the open problems, which I think it's important for you to highlight. We don't know the neutrino mass type, so I will say a few words about neutrinoless double beta decay. We don't know about the neutrino mass scale. I will tell you essentially what are the three techniques we might get to get the measurement, but I will highlight the fact that these three techniques provide three different masses. So it's important to measure all three if we want to understand some physics, the mass ordering, and the Sigma violation. So neutrinoless double beta decay, why it is important? It is important because it is only known process and experimentally accessible process to disentangle Majorana from Dirac neutrinos. There is another known process, but not feasible today, which is the detection of relic Big Bang neutrino. Those might be sensitive to the Majorana nature, because the energy is so low that the effect I have mentioned, that if you slow down a Majorana neutrino, you might get the right-handed component and so be able to disentangle. It could be possible with the cosmic neutrino background, but this is for the far future. Today, it's already hard enough to detect neutrinoless double beta decay, even that in principle could be done, but we did not succeed yet. So it's very important that we insist on this process, which is the emission of two electrons without the neutrinos. Why it is interesting? Well, first of all, you maybe remember this morning when I said, when I was discussing the source and the target, and I said that there is a propagation, and Neutrino-less double beta decay is a propagation over 1/3. It is what is in this diagram. You have one nucleon, a neutron, that becomes a proton through charge current interaction. Another neutron becomes again a proton, but using Dirac neutrinos, this propagator is illegal, so you cannot do it. With the Majorana neutrino, you can have this propagator, and this propagator will be proportional to m/e, which is the mass of the neutrino divided by the energy. The energy is the q² momentum, which is of the order of 1 MeV, and this means that this propagator will contribute a factor that is proportional to m/e, which makes the amplitude proportional to m/e, which makes the rate proportional to the square of the mass. Of course, this makes very clearly that this effect will be very small, but it's not impossible. Of course, it does not happen at all if it is a Dirac neutrino, while it may happen, and it's proportional to the mass, to the square of the mass, if it is a Majorana neutrino. The case of with the two neutrinos is possible in both cases. So this is a benchmark to prove that your experiment is working. If you don't see this, you have no chance to see this, but this is not teaching us anything in the sense that this is a normal standard model process with the second order of interaction. This is a forbidden process with the Dirac neutrinos. It is a perfectly valid process with the Majorana neutrinos. Clearly, if this process is observed, lepton number is violated, so we have found the first process in which the absolute lepton number is violated. So it is the only process that can distinguish Dirac and Majorana neutrinos. Let me say, because this is also motivates search for those who want to do it, but I think that even if neutrino is Dirac, you could observe this effect. It would mean that it's not mediated by a neutrino, but it's mediated by something else. So observing the neutrino-less double beta decay implies anyway new physics. And a theorem says that even if the main diagram is not mediated by a Majorana neutrino, if the effect is observed, the neutrino is Majorana. This is technical, but just to stress that it's not obvious that this is the only diagram contributing to this. There could be new physics that contribute to this diagram. But a theorem proved by Josevalle and others said that if you observe the decay, regardless if this is mediated by a Majorana neutrino, the neutrino must be a Majorana factor. Sensitivity of next generation experiments. So this is not a very updated plot. It's a 2017. There might be some updates, but this is the scenario in which we have the sensitivity of various experiments with germanium, with tellurium, and with xenon. I will cover in a moment which nuclei are interesting, but they will cover more and more the sensitivity in terms of background and in terms of exposure, and they will cover the possible neutrino mass range. Today's experiment are excluding masses of the order of 50-60 million electron volt for the electron neutrinos. I will tell you exactly what I mean with these numbers. Next generation experiment aim at excluding the region around 10 or 20 million electron volt. Main next generation experiment will use liquid xenon, which is the case of EXO and NEXO. or xenon dissolved in a liquid scintillator, which is the case of Kamlan. Then they will use gas xenon in the case of next. In the case of tellurium, the current experiment is Cuore. Snow Plus is using dissolved tellurium in liquid scintillator. Next generation Cupid, this is old because Cupid will not be anymore with tellurium, but will be with molybdenum 100, but this is again the scale of the sensitivity. While germanium experiment, the main experiment is the Gerda experiment, the Legend 200 at Gran Sasso, which are now running, and then the next generation experiment will be 1 ton of germanium detector. Hopefully it will be in Gran Sasso with these sensitivities. Not so many nuclei can be used for neutrinoless double beta decay. The one in red are the okay. But the most popular and most interesting are germanium-76 because the germanium technology is beautiful, and so it's very neat and effective to do germanium detectors with the enriched germanium-76. Xenon is very good because it's cheap, it's easy to enrich because it's a gas, so it's a very popular candidate. Tellurium is okay because it's very abundant, so it's easy to use and it's relatively high energy. And molybdenum is the new coming of the next generation. Many others can be done, but they have various troubles. Particularly, for example, calcium-48 would be fantastic, but it's extremely rare, extremely hard to enrich, so it's not as fantastic as it could be from the point of view of the nuclear physics. Of course, uranium is radioactive, no way. Neodymium is very difficult to enrich. Cadmium is toxic, so depends on the element.
Marco, you said xenon is cheap. Was it a typo, or you mean compared to the other? No.
No. You're right. No, xenon is not cheap as a material, but it's cheap to enrich. I was talking about enrichment. No, you are right. The raw material is the opposite. Germanium is cheap, xenon is not. Molybdenum is in the middle. So I think there is a theorem which is conservation of truffle. Whatever you do, each isotope has some virtue and some problem. So many experiments are choosing different isotopes. This is the summary of what I said. Again, cheap to enrich, not cheap to buy. But of course, whatever you do, you have some problem to overcome. In principle, a neutrinoless double beta decay experiment is very neat. Many times people show this picture. This picture is absolutely misleading today because this is a principle in which you have the two neutrino beta beta and the peak. But today sensitivity is such that usually this peak is well within this tail, and if you don't have a beautiful, this is with infinite energy resolution, then depends on the technology whether this peak can be separated easily from this two neutrino beta beta. Of course, it's more and more important to get the energy resolution so this peak can be somewhat separated, but is never as nice as in this plot because the resolution effect overlaps the expected signal with the tail of the two neutrino. Besides, of course, this is what you get with zero background. Then, of course, many experiments have several radioactive backgrounds, and the problem must be faced. Of course, I assume you will get some dedicated lecture to beta beta. I have mentioned on the fact that there are 3 methods to measure mass. They are here, but I also said that they measure 3 different things, and this is very interesting. I have said before that I was I was talking about the electron neutrino mass. It's not a mistake, it's a definition. The electron neutrino mass is this one. It's a very well-defined thing. What does it mean? This is the effective electron neutrino mass you have to put into the beta decay experiments in order to get correctly the kinematics. As you can see, is a weighted sum of the M1, M2, M3 masses weighted by this mixing matrix. If you look at gravity, which you do if you try to extract neutrino masses from cosmological observation, the cosmological observation of the measurement, for example, that done by Euclid experiment, but also Vera Rubin observation, you observe the distribution of the galaxies in the universe as a function of the distance, which means as a function of the cosmic evolution. You do a very precise measurement, and you try to fit with cosmological models, and you might be sensitive to the contribution of neutrino masses. If you do that, what you measure is really the sum of the three masses, M1, M2, M3, and so you measure this. If you do the measurement of the kinematic of tritium beta decay or another beta decay, so you measure the effective electron neutrino mass, you measure this quantity. If you detect neutrinoless double beta decay, when I said that you are sensitive to the square of the mass, you are sensitive to the square of this mass, which is the beta-beta mass, which is not, it's different from this one, but also different from this one. Because this is the square, the modulus of this quantity, and the weight is the square of the mixing matrix element. But recall you, the mixing matrix element is a complex matrix. So these squares can be negative, and you could have cancellations. This is bad. But you're also sensitive to the Majorana phases, which is good, because this is the only quantity in which you can be sensitive to Majorana phases. So I said, and I repeat it because I think it's right, it makes a lot of sense to try to do all three things. Who says that we should focus on this or on this or on this makes a mistake, because the three information are complementary, and clearly you have a direct measurement from gravity, which is good, but you want to be double sure that you understand the physics, and this would tell you very much information, because this can be, if you know this, you can somewhat predict this, because these matrix elements are known, and if you know this and this, you can extract the Majorana phases, and you can extract CP violating effect. So it's going to take probably one full generation to do that. I don't know when, which of the three will come first, which of the three will come later, but I think the community should push on all three. The most important effort on the direct measurement of effective electron neutrino mass is the Catherine experiment at Karlsruhe in Germany. A beautiful spectrometer, an electrostatic spectrometer, in which there is a fantastic source of tritium source. You get the electron. There is a trick so that you use an electrostatic potential to decrease the energy, to select only the end point of the energy. Then you accelerate again in the electrostatic selector, and you bring the electrons to the detector. I'm not entering into the details, but with this trick, you can effectively study a huge amount of decays by measuring only the final part of the Curie plot spectrum and measure the effect, the kinematic effect of the mass. Last few words on the delta CP, why it is important. Well, it is important for the reason I mentioned. You see now the formula. I told you some time ago that CP violator requires all angles to be not zero. You see here very neatly. We have the sinus of theta 1, 2, the sinus of theta 2, 3, the sinus of theta 1, 3. This is called the Charles-Cold invariant. It is the quantity that drives CP violation. The reason why the quark CP violation is small is not related to the small delta CP. Even for quarks, delta CP is not that small, but the angles are small. So J max is small. So CP violation in the quark is suppressed. It's 10 to the minus 5. While for the leptons, the J max is 10, it's 3 orders of magnitude bigger. So in principle, leptons could explain the CP violation of the cosmological problems. It's not obvious, probably they do not explain the whole thing, but understanding CP violation could bring important information on the matter-antimatter asymmetry of the universe, which certainly is not due to quarks. We don't know if leptons are playing a role. Let me say that to explain a matter-antimatter asymmetry, you also need the baryon number violation, which we discussed, which does not come from here. So you need anyway additional physics if you want to explain that. And that's it. Sorry.
Thank you, Marco, for this very nice comprehensive overview. So now it's time for questions, both on the first part in the morning and also this one. Please.
I have two questions. So for the Opera tau neutrino appearance experiment, what was the signature? So was it then neutral weak interactions or?
It's very technical. The Opera experiment was based on emulsion technology. So, and it was a hybrid detector. So the concept was you take data. When you have a candidate tau neutrino interacting in bricks of lead and photographic emulsion. So there were 100,000 bricks like that. And these bricks were surrounded by an electronic detector. Every time there was an interaction, the computer system identified which brick was hit. And then periodically, a robotic system went to the experiment, extract the brick. The brick was brought into a lab. You open the brick, you look at the microscope at the emulsion, and you look for the track of the tau neutrinos produced by the tau lepton produced by the tau neutrino interaction.
So it's really like so it's a charge current.
It's a current, absolutely. Without a charge, you have to look for the tau lepton produced by the tau neutrinos if you want to be sure it is a tau neutrino. Neutral current interactions are not sensitive to flavor.
Okay, and maybe a little bit building up on this, I know that the sign for the M12 mass is determined by mass effects from the sun. So we know the sign for M12, right? Because of meta effects.
What do you mean, the sign of M12?
We know that M12 is larger than 0, but so we have this inverted and normal order problem, but we know that.
No, but that is by definition.
Yeah, I get this, but we have the sign from M1 to M2.
No, M1 is less than M2 by definition. You call M1 the lowest of the two. It's not because the sun tells you the sign. The oscillations are, let me go to oscillation formula, but the oscillation formula is always depending on the square of the.
It's the matter effect that tells you that.
So where I'm going is, can we not also then?
No, okay. You are saying if I look at all solar neutrino spectrum and I study the MSW effect, then I get this. Yes.
Yeah. So where I'm going to is like if we have clean muon neutrino sources and we can detect tau neutrinos by itself. Can we not also just implement some meta effect in between and get the sign right for M13?
Yes, and this is what the Dune experiment will be able to do. They don't need the tau. You can go to muon to electron. And the Dune will be able to disentangle both the matter effect and the SiP revolution. Hyper K will not be able to do it because the distance is different and the energy is such that the two effects are degenerate in Hyper K.
How do we implement the meta effect? What's the idea? How will you do this?
I don't know. You have to do the calculation. I mean, you send the beam through the Earth. The rock of the Earth is relatively well known. You compute the effect of the matter effect, and the effect of the matter effect depends on the mass ordering. So you can disentangle the mass ordering from the shape of the oscillation pattern.
So by going through the Earth, you get the meta effect for free, and then it's guaranteed that you will bring the answer for normal or inverted.
Yes, it's guaranteed. If it works as expected, yes, it is guaranteed because the two effects are very well disentangled in the sense that the energy dependence of CP violating effect and mass ordering effect are sufficiently different to be separated, which is not the case for Hyper K. Hyper K has a little degeneracy, so they will measure delta CP, but they will need the mass ordering from another experiment.
Okay, thanks.
Other questions? I recommend you to make questions now because Mark is leaving right after the talk and he will not be available tomorrow for the dedicated question time. So
I am sorry.
for very important exactly for the stuff. But so please.
I will be happy to stay here. It would be nice.
I'm sure.
It would be nice.
So regarding the supernova neutrinos,
Yes.
there was this supernova last year, I think, was the closest since 10 years. Was there something?
Oh yeah, but close. Universe is big.
Yes.
So for current generation detector, only galactic supernova or Magellanic Cloud, which is our courtyard, is okay. Hyper K, I don't know if there is some Hyper K guy here. I think that they might detect some events from an Andromeda supernova, but I'm not sure. But if they do, they just get one or two events, which would be nice, would be very fancy, but you don't do much with a few events. So that's the science. Future generation detector, I don't know, but the distance, I mean, the flux go down by the square of the distance. Large Magellanic Cloud, a small Magellanic Cloud, have a distance of 100 kiloparsec, 50 kiloparsec. Andromeda is 700 kiloparsec, so the distance is 14 times. The flux is 14 squared. So it's immediately a factor of several hundred, but yeah, this means that probably they could detect some events from an Andromeda supernova, probably, but not much. I mean, the one beyond Andromeda is again a factor 3, 4, 5 more distant, so you immediately lose the sensitivity.
One question on coherent velocity nucleus catchment. It said coherency requirement was 50 MeV. But I remember for germanium it's more like 20 MeV, so I was wondering where does this 50 MeV come from? That's the
No. If you have neutrinos from stopping pions, the energy of the neutrino is a monochromatic neutrino over 50 MeV.
But then the interaction is not necessarily a fully coherent interaction.
You might have some you have to be careful in extracting the coherent scattering. Yes, the 50 MeV neutrino can also break the nucleus or have a non-coherent interaction with a single nucleons. Yes, you're right. In the data analysis, you have to separate the coherent scattering with the nuclear effects. Absolutely, yes, you are right. It can be done doing properly the analysis because the two effects have a different energy dependence of the scattered nucleus. Again, it's a compromise. To avoid the nuclear effects, you should stay below nuclear binding energies. So you would like to have 10 MeV neutrinos, but you have two problems. First, the stopping pions will give you 50, and if you want 10, you have to invent a way to do 10, but then it would not be a monochromatic one, which would bring other difficulties. Second, you don't have flux probably, so you you also decrease the recoil momentum if you decrease the energy. So it's always a compromise. Let me say, using stopping muons from neutrinos from stopping pions is a very clever idea, because you can get very high flux, because it's not difficult to produce many pions, and being monochromatic helps a lot, because it's not difficult to disentangle what you have in mind if the neutrino is monochromatic.
So, like for example, the power plant, we would have neutrinos below.
Yes, but not monochromatic at all. They would be anti-neutrinos and not neutrinos, which change the cross-section a little bit. But so you have a spectrum. You can imagine a coherent neutrino scattering with the reactor. Yes, but you have to live with a broad energy spectrum of the neutrino, which makes your life harder. You don't have the problem of the breaking nuclei, but you have less recoil and less precision because of the broad energy range.
Any other question? So we thank Marco again.
Thank you very much.
So now we have the coffee break. Before going to the coffee break, that will last until 5 p.m. So we have some time more. We will reconvene here at 5 p.m. for the speed talk session. So take some rest and be ready to talk about yourself in 90 seconds each, which is important because you cannot be longer, otherwise we are lost. But please do not be too short, because we want to hear from you. Two other very quick points. One is about the slides. The slides of today are already on the Indigo website, so you can find them. And tomorrow we will have the first session on statistics and then so on. So be sure that you have already the environment set up. Otherwise, you can ask help to Knut Mora over there. Again, raise your hand again. Okay. So enjoy the coffee break. Bye.